size is huge. I am posting on my YouTube account, then you will see today evening that for each lecture that I upload, so I have also a link that you can click on it and take a look at the video, okay? So, all right. So in the previous class, I introduced you the gradient of a scalar field. And basically the whole idea was that we are looking for directional derivatives, right? So when we have multiple coordinates, right? So coordinate components, we always ask this question, in which direction we are calculating the derivative. And over there, you saw that always we need to set a direction. And when we worked out these derivations, we saw that, okay, so we see some quantity here that is basically is a dot product of the direction and derivative of the function, okay? So derivative means that that's the del operator over there, and you go basically calculate the derivative with respect to each component of the coordinate system that we have. Then we said that that is a gradient of a scalar field. Obviously, it's a vector. So once gradient is applied to scalar, it makes it as a vector. Okay, so it increases the order by 1. So this is very important. The gradient of a scalar field is a vector field. So you can apply gradient not only to scalars, but also to vectors, right? Do you recall seeing a quantity like that? In those people working on mechanics or fluid mechanics, they should have seen something like that. Gradient is applied on a vector. Let's say I have vector V, right? So something like this. So first of all, what is that? Is it a vector? It's a vector? The whole thing is a vector? Okay. So you say this is a vector? No? What? It becomes a tensor. Okay. So if you're in the, let's say, we are in XYZ coordinate system, right? So if I consider this, it is going to be d dxi, right? Vj, so I will write it like this, to Vj ei ej. It's a tensor, second order tensor. How many components you have? 9 components, right? So that's how it is. So one famous one is the gradient of a velocity field. If you know Navier-Stokes equation, how many of you know Navier-Stokes equation? You have seen it, right? So there's a term over there that basically has in the Navier-Stokes, so I will write it here. So you have a bunch of different terms, but one crazy term is this one, V dot del V. Usually on the left-hand side of the equation, right? And often we say, oh, it is 0. But that second part of it, it's a tensor. It has 9 components. Okay? And that part actually, when you have it in your problem, when you solve fluid mechanics problem, if you have that, if you retain it, makes the calculation significantly difficult. Okay? The analytical calculation or also numerical calculation. very difficult. So it is not only limited to scalars. So you can apply it to vectors, you can apply it to tensors. So it's an operator. It's a vector operator. Okay, very good. Then you have vector fields. So these are vectors that depends on the different position coordinate that you have, q1 to qn. Basically, you can have like a velocity field is a vector field, electric field, force field, doesn't matter. So key point is this vector field that you have gets x, y, z, or time, and also gives us x, y, z, time, or more components, right? So we all put it in the vector. So obviously they have magnitude and direction. So this is not something new, right? We knew it. Okay. Now, so these are very important because now we can define flux of a vector field. Okay. So the flux of vector field is defined as the amount of the vector field V goes through a surface S. Let's say I have surface S, closed surface like this. So this is my surface S, and I have this vector A is going through it. Okay, so the whole space you can see it. So if we want to understand how much of this basically V field goes through surface S, so we define that quantity, let's say call it phi, it's flux. Obviously we need to sum it up over the area that we have for the surface, okay? And usually this vector n is defined as perpendicular to the surface. So think about a sphere. So if you want to find the flux of some quantity, let's say, I don't know, heat flux. So for some reason you have a heat source at the center of the sphere, and you want to see what is the flux that goes out, right? How much heat is going out as a summation. So basically you're calculating that integral. Basically you're looking at the flux at the point, then dotted by the normal vector to the surface, which you are supposed to derive it, times ds, which is the element of the surface. So ds is the surface element. So surface element definition depends on you, what coordinate system you are using. If you are in the XYZ coordinate system, say you have a surface all in XY plane, so this is just going to be dx dy, right? So let's say I have surface something like this. So that is my surface element, dx dy. And you can change it, right? So that is not significant. Sometimes people write this part as ds vector. Okay, so you will see both of this representation. So ds vector means n ds. And ds, if I write it like the first one, it's just a scalar value. It's a magnitude. There is no directionality in it, and I need to basically add this n. Yes?
Because there is a dx, dy, and no ds, there are two integrals over there.
Yes, it's a surface integral. It's a surface integral. So in two-dimensional, it's going to be 2. All right. So n is a unit normal to the surface. Usually, if you have a volume and you're looking at the surface, it goes outward. So it is not defined inward, it is an outward. vector, okay? All right, so now we know the flux of a quantity, flux of a vector. Then, if I think about this basically property, and the surface S that I'm going to consider. So if I basically consider a 3D object, which has a volume V. So let's say this has a volume also like V. And I'm going to calculate this flux at a very small volume. So I'm going to squeeze it to 0 volume, okay? So you can think about that at that point, I am looking at the basic point flux, right? What we call it as a strength of the sink or strength of the source, whatever comes out from that point. Okay, so you understand the physical meaning here? So for that case, basically, we can show that if I calculate the divergence of A, so this is called now divergence, basically a dot product of the del operator with your vector. That equals to that limiting flux that you are going to get. It is very important. Okay, so what is the divergence of A here? So if think about A is like A1 I plus A2J plus A3K, basically the divergence of A is going to be d dxi AI. That's the divergence of A. Einstein summation. Right? So the divergence of A, as A is a vector, is a scalar. So you can think about you are doing a dot product between two vectors. Nothing special. So the same principle applies here. It always is going to give you a number when you're applying it on vectors. Okay? So this divergence of A is going to equivalent to this flux that you have for a very small volume of the basically material that you're considering. Very small. So that's the basis of the divergence theorem. So if you basically consider it in an integral form, sum it up over the whole volume that you have, basically it tells you that the flux of a vector field that goes through a closed surface is equals to the divergence of a field inside that volume. Okay, so think about it. If the F corresponds to some flow, so basically this gives you the net rate of flow going out of surface. This part gives you the strength of source or sink that you have at a given point. So the analogy here I can give you to understand this equation is like this. Think about we are sitting in the class, right? All right, so at any point, I can either basically look at the number of the students in the class and also count the number of people coming from these two doors, right? So the number of the people coming from two doors are going to correspond to that net rate that I have on the left-hand side. So that gives me number of the people here coming out or getting out of the room, right? Or I can ignore that, I don't look at that, I look at you here, and I look somehow magically some people are appearing and disappearing. Basically, it says that the number of the people are appearing or disappearing is the same as the people are going out or coming in. That's it. Obvious, right? It should be equal. That's the meaning, physical meaning of it. So whatever goes out or comes in from your boundary, it should match with the production or consumption that you have in whole volume of the system that you are considering. Is it clear? Good. So here ds, basically be careful, this is just n hat dot n hat ds, right? So you need to be careful with that. So this one I need to fix this. This shouldn't be A, this should be F. Sorry about this. A was in the previous. And this guy also, it should be F. So in the curvilinear coordinate system, what you need to consider is that this divergence part, you need to consider the scales. 1 over h1, h2, h3, and basically when you are calculating derivatives, also you are going to have h1, h2, h3. Okay, so it becomes a little bit more involved because your scales are not 1. In a Cartesian coordinate system, you remember h1 equals to h2 equals to h3 equals to 1. Right, so that's much straightforward. But that's not a big deal, so we can have that. Okay, so let's consider this. So think about, we have a rectangular box or room with a dimension of 2 times 3 times 1 meter. So maybe the height is a little bit low as for a room, as 1 meter. So let's make that 2 meters. Yeah, if we make it at 2 meters, it's going to be similar as the small room we have in the 4th floor. Great. Okay, so we have a steady flow field of heat given by that equation. For some reason, our AC system works based on that. It generates heat at different location of x, y, z based on that. So the units also are per joule. And we want to use the divergence theorem to calculate the total heat flow out of the room. Okay, and depending on the sign of this quantity, we will judge whether we are losing heat or we are gaining heat. Okay? So the divergence theorem, it says that F dot ds equals to V dV, which is the volume. So we are looking for this side, right? That integral. Do you know how to calculate that integral here? Let's say if we didn't know the divergence, the reason that we're using divergence theorem is that it's easier. If you didn't know the divergence theorem, if I ask you what is the total, basically, heat flux that we have, how would you calculate it? So you need to calculate the left-hand side. And how would you do it? Basically, you will select different surfaces. It's basically the dimension of the room. So you have x, y, y, z, and x, z planes, each of them 2, right? So you have 6 planes. On each plane, you are going to calculate that integral. Do you follow that? No? So the point here is, I assume that we know how to calculate f dot ds integral. How many surfaces that we have here? How many? 6 surfaces, right? So it's something like this, right? So it's something like this. So you need to define this normal vectors n1, n2, n3, and 4, 5, 6. And on each surface, you want to basically calculate f dot ds, right? Then calculate the integral for that surface. So it's a 2-dimensional integral. Then you sum it up over all the surfaces, all 6 surfaces. That is going to give you the total heat flux. Right? So that's the normal way of doing things. We don't want to use that. We want to use divergence theorem. It's easier. So what we are saying that it is a closed box, right? So what I'm going to do, I'm going to calculate the divergence of F. I know my volume element. It's a rectangular coordinate system. So dV is just going to be what? dx, dy, dz. Check the equation that we have, h1, h2, h3, dq1, dq2, dq3, right? That's it. So if we can calculate the divergence, then we're good. So, all right, so what is the divergence? So you tell me. So that's the, you need to calculate that, right? So this is going to be, based on the notation that we have, df1 dx, df2 dy, or you can think about it as an x component. Let's stick to x, y, z. Y component plus z component, right? So what is that? So this is the x component, y component, and z component. Mm-hmm.
So if we are differentiating with respect to x,
Mm-hmm.
so will it just be 1?
1.
Yeah.
So the derivative of the first component with respect to x. 2, not 1, 2, right? What is the derivative of the second component with respect to y? 2xy. And the third one with respect to z? Okay, so this is going to be 2 plus 2xy plus 3, right? So I will write this as basically 5, right? So it's going to be 5 plus 2xy.
That dx, dy, dz will be equal to 1.
No, why 1?
Because h1, h2, h3
What?
as you said for h1, h2 and h3.
No, the volume element is going to be dv equal to h1, h2, h3, dq1, dq2, dq3. And Q1, Q2, Q3 is the coordinate components that you have. It's x, y, z, r, theta, phi, or whatever. Right? So that's why it becomes dxy, dz, basically. All right, so now we are going to work with the right-hand side. So let's call this as a phi, our flux. It's going to be integral over the volume of my room, 5 plus 2xy dxy dx dy dz. Okay? And how do you do this integral now?
Assign the limits.
Yeah, assign the limits, go one by one, right? This is the easy one, right? So you don't need to do any, we don't need to do any crazy thing here, right? So just assign the limits. So my z goes from 0 to 2. For the other one is 0 to 3. And I think x is at from 0 to 2. So it will be 5 plus 2xy dx dy dz. So you go one by one, right? So integrate with respect to x, apply the limits, then whatever you get in terms of y, apply the limits, and z, apply the limits. So it's going to give you a number. So that's the whole point. So divergence of a vector, and if you have even integrated, it's not going to change the basically scalar vector. It's just always going to be a scalar. So if you do this, you will get as 48. So you can do the calculation. So it's a positive number. So that's the whole point. So what does positive number here means now?
It's going into the room.
So it means that I have a source. So it is radiating heat outside. Okay, so it is giving heat out. And you remember the way we defined the normal vector was also outwards. That's the direction of the positive here. Okay, so this was one important vector operator that we had, right? So divergence. Yeah.
I got 48 after the second integral. So after
Oh yeah, oh, sorry, I changed the z by factor of 2. You are good. So it's going to be multiplied by 2. Good, yeah. Because the last integral was from 0 to 1, so it's not changing. Right? So it should be multiplied. Yeah. Very good. All right, so the first one was the divergence, right? So now another important one is the curl. Have you heard about curl? Curl of a vector field? Some of you have heard about it, right? So, okay, so this we don't need it. Curl of the vector field. Basically, it represents a local rotation that you have in that vector field. Okay, so think about a shear flow, right? So shear deformation. You also apply rotation. At the same time you are doing shear, the rotation is being applied, right? So the way that we calculate the curl, it's a cross product between the del operator and the vector v. So in the Cartesian coordinate system, it's pretty straightforward, and we mainly are focusing on this. So you can write it in terms of the determinant, right? First row is going to be basically the direction of the basis that we have, E1, E2, E3. Second row is d dx1, d dx2, d dx3. Third row is going to be components of your vector, v1, v2, v3. Okay, so if the curl is basically positive or negative, means that there is a local rotation happening, either counterclockwise or clockwise. If it is 0, there is no rotation. So you have an irrotational field. Some of the deformation you apply to materials are irrotational. So think about the case that you apply shear deformation, right? So let's say we have a shear flow. So do you remember this example in the fluid mechanics? So you have two parallel plates. You're moving the top plate with a velocity equals to V0. Bottom plate is stationary. And here you have your fluid, right? So let's say you are in a steady state. Your fluid is Newtonian. Do you remember what was the velocity profile shape here? So let's say this is my coordinates. So let's live in the two-dimensional coordinate system XY. So I'm putting it 0 here. The distance is h. Yeah. So do you remember what was the velocity profile? Yeah. It was a linear velocity profile, right? So on the top plate, you have the velocity as the V0. And as you approach to the bottom plate, because you have no slip at both plates. No slip condition means that liquid at the boundary, at the solid boundary, is going to stick to your surface. So the velocity of the liquid and the surface are going to be exactly the same at the boundary. So on the top boundary, I am moving with the velocity of wall. On the bottom boundary, I'm going to be stationary. So I'm going to be sheared continuously. Right? So if I draw it, so this is a typical basically velocity profile you have seen. So the equation for this is your Vx is going to be V0 divided by h times y. Okay, does it make sense? Basically, that's the equation of the line. I haven't done anything magical here, right? So that's my Vx. So let's say my velocity profile, there is no other perturbances here. So I have vector like that is my x component. And the other ones are 0, right? So nothing happens. Very boring type of fluid. So can you calculate the curl of this vector field? It's a vector field, right? So at each point, basically I have a different velocity. So if you use that relationship over there, so what is going to be your curl? So let's do that. So E1, E2, E3, ddx1. So let's write it in terms of ijk because over there I have I, j, k. So this is ddx, ddy, ddz. The first component is v0 divided by h times y, and these are 0. Okay, so can you quickly tell me what is the curve? If you calculate this determinant. The I component is going to be 0.
Just J component.
J component is going to be what?
V naught h by d. V naught h by d dz multiplied by V naught h by V naught by.
Okay, so let me write this. How many of you know how to calculate determinants here? Most of you. Okay, so let me write. I will write it here. So usually, what we do, we will expand the determinant. So we will talk about it in the matrix. There will be no ij component, only k component is going to be there. We will talk about this, but we are going to use expansion. So we are going to expand it with respect to basically this ij component. So if you, okay, let me, yeah. So the I component here is going to be zero, zero. So this is going to be 0 minus j component. So for j component, we are going to use this submatrix that we have. So if you don't understand it, that's okay. So you will see later. Okay. So all of these things are going to be 0. What? J is 0. Why is not? I'm calculating derivative with respect to z.
Why not we start from the last?
What?
Why
Oh, you can start with the last. I wanted to write to show you it's 0.
So J is 0 because the derivative of y with respect to z is 0, right?
Yeah, yeah. There is no z term in it, right? So, it's 0. So you are going to have the last one, right? So the last one is what? What is it? d dy v0y divided by h? v0 divided by h. So that's my rotation I'm going to get from this flow. And it is in the k direction. So rotation is happening in the xy plane, right? That's how we define rotation, right? So the plane is xy, but the perpendicular vector that is basically normal to the plane of the rotation is in the direction of, actually in the direction of minus k, right? So if that's basically xy plane that I have, so I have the rotation like this, okay? And it makes sense, right? So think about you have some sort of dumbbell in the shear flow, right? So as soon as the y position of this dumbbell changes, right? So let's say it becomes something like this. This part is facing more shear displacement than this part. So it cannot stretch. What will happen is it's going to have this tumbling motion, rotation is going to happen. That tells you. So you can basically generalize this to different type of deformation. It's the same story, right? So you can calculate the curl of a force field and see how it rotates. So basically using the Einstein notation in Cartesian coordinate system, basically it's the same thing. So you use epsilon ij. So this basically we are treating it as the index notation that we have, right? So you should be able to use that type of the notation to do some simplification or proof of some identity involve this del operator, okay? So if you are in a generalized curvilinear system, I will add one constraint that it's orthogonal curvilinear system. I don't want to go into the non-orthogonal ones because it becomes more crazy, but that curve, basically what you need to consider is the magnitude of the scales that we have, h1, h2, and h3, okay? So those are now coming into the play. But as long as we are in an orthonormal coordinate system, we don't need to worry about that, so we can use this. And here, just one important point, given that I'm repeating the indices here, J, and K, this is the only time that I don't mean summation. So I'm not using summation convention here for that particular formula, okay? So it's not that very important, but just for some reason, if you want to calculate a curl in other coordinate system with scale factors that are not equal to 1, so you can use that. Okay, so similar to the divergence theorem that related to the flux, right, to the strength of the sink or source that we have, we can have similar theorem that basically sums up the rotation of the vector field on a boundary and the surface. So that is called Stokes' theorem. So have you heard about this theorem, Stokes' theorem? Usually in calculus we have this. So basically it relates the surface integral of a curl of a vector field to a line integral around the boundaries. So now we are only considering one-dimensional. So this is, let's say, a surface that I have C. Basically, a boundary is a C. It's a closed boundary, and it has a surface of S. So basically, it says that total amount of rotation that you get over a surface S is just equal to the net rotation that this field has at the boundaries. Other internal rotation, they cancel out each other. So you just need to consider the rotation in the boundary to get the total rotation happens inside your surface. So that's the meaning of it. So rotation of a field, so I just told you it's a curl. Curl gives a rotation. And you're summing it up for all the point in the space that you have. All the point of the surface. So the right-hand side basically tells you, okay, I'm just going to calculate the whole rotation. But instead of that, we can only consider the rotation that this force or whatever F or field has on the boundary. So that's the beauty of the Stokes theorem. So let's see in one example how we can use this. So we want to verify this Stokes theorem, right? So we have a field, vector field. It's in the XYZ coordinate given like y minus xz. So basically this is equal to yi minus xj plus zk, okay? So this is my vector. And the surface I'm considering, it's a hemisphere. So if I can plot it here, x, y, z. So I'm considering the surface of this, okay? So do you get the geometry, what we have here? It's a half sphere on the positive side of the z. Okay? So this basically the equation for the surface is x squared plus y squared plus z squared equals to 4, meaning that its radius is 2. And if I want to have basically a circle here, so this is in a 3-dimensional space, so my drawing is not very good. So this radius is also 2, right? If I cut it from the center, the the radius of that circle is going to be equal to the radius of the sphere. So that means that C boundary. So this is the C boundary that I have. Okay, so how should we proceed to verify the Stokes theorem? Basically, the integral on the boundary, the whole. Basically, this means that is on the whole boundary, this circle that we have on the integral, one-dimensional integral around this contour of this basically space that we have. Any suggestion?
Start with the curl.
Start with the curl, okay. So what is the curl? So the curl, you can calculate it quickly here. Okay, d dx, d dy, d dz, y minus x, z, right? So this is just going to give you the curl.
Do we need to assume curvilinear coordinates?
No. This is not curvilinear. You can do it in xy. I've given you everything in xy. For integral, sure, you will do variable change, you go to a spherical coordinate system. But it doesn't mean that the representation of the theory is in that coordinate system. So we will stick to the representation of the theory in the Cartesian coordinate system. What is the curl?
Minus 2k.
What?
Minus 2k.
Minus 2k, right? Yeah. Good. So basically, if I want to write it, it's 0, 0, 0, minus 2, right? So, something like that. Okay, so then, all right, let's do this. So we need to calculate this integral on the surface of this hemisphere, so outer surface that we have. How do we define ds?
dx.
Okay, so dx, dy, dz. Alright. So then you need to think about the limits that you're going to consider. So, okay, because the problem also starts when you are going to consider as because this ds is a vector, right? You have n. What is your n then? Normal vector. So how do you define the normal vector? For the surface of this, basically this cap that you have.
Normal vector will just be parallel to the z-axis.
No, it is not. Look at this hemisphere cap that we have over there, right? So normal vector here is going to be this way. Here is going to be this way. Here is going to be this way. If I'm sitting somewhere here, maybe it's like this. So it changes this direction. Very complicated. All right, so if you are in a spherical coordinate system, right, so I'll get back to this. If you're in a spherical coordinate system, how do you define your ds for this problem? So think about it. Here for ds, we have this spherical cap, and we are looking at the surface element at a constant r, right? Do you remember I had a very small discussion that in a 3D dimensional space, you are going to have 3 surface elements. Basically different surface elements, right? So in this case, what I have is something like this, right? So I'm looking at this surface. So this is my ds. The ds, all the points on the surface are at the same radial distance from the origin, which is r, radius of my sphere, right? Okay, so now, how did we define ds?
You can use cylindrical coordinates?
No, not cylindrical. I want to use a spherical.
Oh, spherical.
Spherical, because it's a sphere.
R sine theta.
But in terms of the scales, what was the? You have it in your notes. What? But what is the relationship between ds and the coordinates? So if I'm in the 2D xy, this is going to be dx dy, because it's going to be h1, h2 dx, right? Dy. So I'm looking for that. What was the relationship? So for this particular case, it's going to be your hr, h theta, because r is constant, h phi, d theta, d phi. Okay? That's the magnitude of it. But we need to have this direction, right? So, okay. So for this particular case, you can use basically the same as the definition of the scales, but now you are not only going to basically consider the magnitude, but also the sign of it. So retain the sign too. So that helps. D theta, d phi. Okay, so I'm going to calculate that. And R here basically means if this is my center, R is a position vector that goes to the surface here I have. So how do you define R in this? In this coordinate system? So your R basically is going to be, it's a position vector, right? So let me write it here. You have, as the x component of it is going to be r sine theta cosine phi. Y component is going to be r sine theta sine phi. And z coordinate is going to be r cosine theta, right? So that's the going from the spherical to the Cartesian XYZ coordinate system. So you have three basically parameters, r theta phi, and also you have XYZ. So what is your r value on the surface? 2, right? So consider this. Basically, you have basically x, y, z component of it, right? And your position vector is going to be 2 sine theta cosine phi, 2 sine theta sine phi, and 2 cosine theta. Okay, so this is exactly the same as the XYZ coordinate, but I'm going to use theta phi because it's easy to do the calculation for you. So this R basically points to the surface of this sphere. That's it. Sphere with a radius of 2. So now, if I use this and I calculate the ds, right? So I need to calculate two derivatives. First, dr d theta is going to be 2 cosine theta cosine phi, 2 cosine theta sine phi, and minus 2 sine theta. And another one is dr d phi. So it's going to be minus 2 sine theta sine phi, 2 sine theta cosine phi, and this one is going to be 0. Right? It's a derivative with respect to phi. Last one doesn't have phi. All right, so basically the magnitude of these two things are going to give you, h. So your h theta is going to be magnitude of this. Your h phi is going to be magnitude of this guy. So that if you calculate the magnitude, those are the scales of your coordinates. So now I can basically incorporate these two into that relationship I had here and come up with the expression for ds. And remember, ds is a vector here. So if I follow that, my ds is going to be 4 sine theta cosine phi minus 4 sine 2 theta sine phi, 4 sine theta cosine theta. Okay, still we are living in the XYZ coordinate, but what we have done, we have cast the components in terms of the r theta phi. So that's our ds. So to calculate this integral, I forgot the dot product over there. To calculate that integral, I need to dot the del with ds vector, right? And my del is pretty simple. So xy is 0, yes.
For ds, it will be minus 4 sine square
Oh, yeah, yeah. Okay. So it's going to be,
We're multiplying the x, y, and z.
yeah. Let me double check this.
Oh, to 0. Last term 0.
Oh. Yeah, I made you confused here. Sorry. That's why. There should be a cross. I understand. It's a cross product of two vectors. It doesn't make any sense to have two vectors side by side to give you another vector. It is impossible. Right? I think you were doing dot.
Yeah.
Yes. Yeah, sorry about that. So it should be cross. So this should be cross. So make sure you have that. Okay. So if you do a cross, you will get this. Basically the cross of this two vector dr d theta dr d phi. So you would get that. Then you need to calculate the dot product of ds and curve. Okay? Just dot product. So x component in the x component, y component in a y component, and z component in z component. And you will only have, in this particular case, it was by design, you are going to have one component left. So it's easy. Basically, kind of a simplify. So if I write this here, dot ds vector is going to be minus 8 sine theta cosine theta. Okay, this is great because I can now calculate the integral. So why? Because I can write this as, it's a two-dimensional integral d theta d phi. Theta changes because it's a semi-sphere, so from 0 to pi over 2, this is a polar angle that we have, and phi is 0 to 2 pi. Okay, so that's going to create me half a sphere that I have. So you do that integration. You integrate with respect to theta, and phi there is no dependency over there, so it's just going to be 2 pi. Okay. So this, if you do the integral, it is going to be minus 8 pi. Okay, so this was a difficult part, very difficult. So you need to do some change of variables, figure out what is the surface element, right? So it is not very convenient. Now let's look at the other side of the equation because we wanted to verify it, right? So if I look at from the top, basically in the xy plane, I have a circle like this, right? So I have a circle. This is my x and y, right? And this is the C circle that I have. Radius of it is 2. So meaning that x2 plus y2 equals to 2. And I need to figure out what is f dot dr means here. Along the contour of the boundary. What's that?
I was looking at the circle, you x squared plus y squared equal to 4.
4, yeah, that should be 4. Sure. 2 to power 2. R squared, yeah. So how we should proceed with this guy now? So you have an equation for this guy, right? So with this circle, right? Let's say, because it's a one-dimensional integral, so I need to basically look at the dr means that it's a tangent to the line that I have, and I need to calculate the dot product of f at each point with this vector dr that I'm creating here. Okay, so if you think about as a something is moving along that line, so dr corresponds to the displacement here, right? So instead of doing this, what usually we do, we call it as a parameterization of the path. So instead of dealing with x and y, we are going to use a trick to introduce a third variable, let's say t, usually it is t, to simplify this integral. So what I mean here is that if you think about something is moving here, right? So it's a position vector. Let's say this r is the position vector, okay? So I'm going to define basically r prime of t, okay, as dr dt. And I'm going to basically define r vector as a function of some variable t. So think about this, like, I don't know, maybe time. So if I introduce a variable t over there, right? So currently what we have, if we write it as a vector, r is what? xi plus yj, right? That is r. X squared plus y squared, and yeah, you have the basically radius of 2. So instead of doing this, what I'm going to suggest, I'm going to use 2 sine t I plus plus 2 sine 2 cosine. So these are going to have 2 also here. Cosine t j plus 0 k. There is no k happening here, right? It's 2-dimensional. So whatever t I choose always is going to be on that red line. So it's going to consider all the points on the red line. This is called parameterizing basically the curve C, closed curve C that we have.
For any circle, the coordinates are x, sine, theta, and y cos theta.
You can use theta too. That doesn't matter because I use theta over this. I don't want to use theta. That's the only reason. You can use any variable you want. Okay. So then I'm going to calculate dr dt. Because dr dt, remember, in this, we want to calculate that delta r, dr, right? So my dr is going to be, basically, the idea here is that instead of using dr, I will use r prime of t dt in that integral. So that's what I want to do. So I need to calculate the derivative of this with respect to t variable that I have defined. So if I calculate the r prime, is going to be 2 cosine t I minus 2 sine t j, right? And I'm not going to write the k component.
Minus 2 cos plus 2 sine.
What?
Derivative of sine t will be minus cos.
No, derivative of sine is cosine. Cosine is minus sine. All right, so this is good because now I can compute f r prime, right? So remember, I want to put this here. Can we do that calculation? What was f? So let me write it here. F is this thing, right? Y minus x z, right? So if I do the dot product, I'm going to get? And remember, you are doing that on that circle. What is y on that circle?
Y is r cos t. So 4 cos square t. 4 cos square.
No. You're on kind of a right track, but you're mixing things up. What is f? First component of f is y, right? On that curve, when we have parameterized it, what would be y?
2 cos t.
Okay, so it is going to be, so cosine t. So if I do f is 2 sine t here. So let's see what we have done here. Yeah, I have it in the correct way in my note, but we made a terrible mistake here. So let's say this is the angle T. So that maybe it's better to use. So it's just doing cosine theta and sine theta. So R is going to be cosine, then sine. And this is going to be minus 2 sine plus 2 cosine. Okay? So fix that. That was a mistake. So if we do f dot r prime, so it's going to be minus 4 sine squared t minus 4 cosine squared t, right? So the mistake was the sine and cosine were flipped, right? So they shouldn't be like that. So x component on a circle is cosine, y component is going to be always sine. So I have that expression. So what is that expression? If you want to simplify it. So this is going to be minus 4 sine square plus cosine square, right? 1, right? So it's going to be minus 4. All right, so now let's write the integral. So I have f dot dr. We managed to get it to minus 4. Instead of dr, we are just going to use dt, right? R prime dt. And it's a closed integral, means that we need to sample the whole circle. So your t is this angle is changing from 0 to 2 pi. So what is going to be this integral now? Minus 8 pi. And we got it from the kind of a rough way, minus 8 pi, right? So always when you have this Stokes theorem, you need to think about how you're going to parameterize your path along the contour line that you have. It should be closed path. Basically, there should be a loop, circle, whatever it is. and then you can use this theorem. Okay, so in summary, for this part, so you learned that there's a position vector that depends on the coordinate component Q1, Q2, Q3, and it can increase. So you can using that position vector, you can define a basis vector, and magnitude of these basis vectors are going to give you the scales, right? And so this is for Cartesian, cylindrical, and spherical coordinate system. So you can have the scales, and you learned how to calculate the curve, divergence, and use those theorem of divergence and Stokes theorem to, simplify the basically either flux that is crossing the boundary or the total rotation in your system. So in the next class, I will solve some of the